Take out your phone and look along the bottom edge, right beside the charging port. There is probably a tiny hole there, barely wider than the point of a pin. Now check the top edge or the area around the rear camera. You may find another one. They are easy to ignore and surprisingly easy to confuse with the hole used to eject a SIM tray. Plenty of people have pushed a SIM tool into the wrong opening. So what is it? In many phones, that tiny opening leads to a microphone. But that answer creates a stranger question. Your phone already has a microphone close to your mouth when you make a call. Why would it need another near the top and sometimes another beside the camera? Why does a phone need so many ears when you only have one voice? Let's get into it right here on Small Things. One microphone would seem like enough. At first, one microphone sounds perfectly reasonable. The main microphone is usually near the bottom of the phone. During a normal call, that puts it relatively close to your mouth, where it can pick up your voice clearly. But a microphone does not know what it is hearing. It cannot decide that one vibration belongs to you and another belongs to a passing bus. At its most basic level, it responds to changes in air pressure and turns those changes into an electrical signal. Stand beside a busy road and speak into your phone. Your voice reaches the microphone, but so do tires on pavement, wind against the handset, nearby conversations, and music leaking from a shop behind you. To the microphone, those sounds do not arrive in neat boxes. They overlap. That is the real problem. Your phone usually has no trouble hearing you. In many situations, it hears too much. A second microphone gives the phone something a single microphone cannot: another listening position. The phone listens from more than one place. The microphone near the bottom sits relatively close to your mouth, so your voice often reaches it strongly. A microphone near the top is farther away, which changes the balance between your voice and everything around you. A microphone near the rear camera adds another useful position when you record video. That does not mean the top microphone hears only noise, while the bottom microphone hears only you. Every microphone hears a mixture. What changes is the mixture itself. Imagine a car passing while you are speaking. Traffic may reach several microphones at similar levels, while your voice is much stronger at the microphone closest to your mouth. If a sound is louder on one side of the phone than the other, that difference adds another clue. The extra microphones are not simply backups waiting for the main one to fail. Their positions give the phone information that one listening point cannot provide. But collecting those signals is only the first step. The real work begins when the processor compares them. How your phone separates your voice from the world. The phone can examine how strongly a sound appears in each microphone, whether it arrives a fraction earlier at one than another, how similar the signals are, and whether parts of them resemble patterns found in human speech. With several microphones, it may also gain clues about where a sound is coming from. Think of several people standing in different parts of a room. Each hears the same event from a slightly different position. Compare what they heard, and details emerge that one listener alone might miss. A smartphone does something similar with signals and algorithms. In a busy cafe, your voice may be strongest near the microphone closest to you. Conversation, music, and clattering dishes spread through the room in a different pattern. By comparing the signals, the processor can emphasize sounds more likely to belong to your speech while reducing parts of the background. This broad process is called noise suppression. In some situations, phones also use beamforming, combining signals from multiple microphones to favor sound arriving from a particular direction. It is not perfect. Strong wind, a nearby shout, or another person speaking close to the device can still confuse the system. What matters is that no microphone has to know what noise is. Several imperfect recordings can become far more useful when the phone compares them. Those microphones do more than phone calls. A phone call is only one situation where those extra listening positions matter. Put the phone on speaker and the geometry changes immediately. Your mouth may now be several feet away, and the device could be lying flat on a table. The sound source has moved, so the phone has to work with a very different acoustic setup. Then turn the phone around and start recording video. Now the sound you care about may be in front of the camera rather than beside your mouth. Depending on the device, microphones around the phone can contribute to stereo recording, directional capture, or other processing that helps the audio better match the scene being filmed. Outdoors, there is another problem: wind. A gust can create heavy turbulence around one microphone opening while affecting another differently. That variation can help the phone recognize that part of the signal as disturbance rather than useful sound. The strange microphone locations now make more sense. A smartphone keeps changing jobs: phone, speakerphone, camera, recorder. The hardware is spread around the device because the device itself is constantly changing how it is used. And that creates a very human design problem. Some of those openings look almost exactly like the hole for the SIM tray. What happens if you poke the wrong hole? One hole is designed for a metal pin, the other is not. Fortunately, the sensitive microphone component is not always sitting directly behind the opening you see from the outside. Inside many phones, sound travels through a small acoustic channel before reaching the microphone. Along that path, there may be mesh, seals, or gaskets that help protect the opening and preserve the acoustic path. In some designs, the channel bends rather than running straight inward. A SIM eject tool pushed into the wrong hole may hit part of the internal structure instead of driving directly into the microphone, but that is not a guarantee. Different phones use different layouts, and a sharp tool can still damage mesh, seals, or other components. The fact that engineers anticipated the mistake does not make it safe to test. Before inserting a SIM tool, look for the outline of the tray itself. The eject hole belongs to that movable tray. A microphone opening usually sits separately in the phone's frame. Even the opening itself has a job beyond simply being a hole. Its size, path, and protective layers have to let sound enter while helping delicate parts survive dust, moisture, and everyday handling. That leads to another surprise. The microphone behind the opening is much smaller than most people imagine. The microphone is smaller than you think. Modern smartphones commonly use MEMS microphones, miniature sensors made with microfabrication techniques similar to those used for computer chips. Inside one of these microphones is a tiny diaphragm that moves when sound pressure reaches it. Electronics then turn that motion into a signal the phone can process. The scale is what makes the design possible. A phone has to fit cameras, antennas, speakers, vibration motors, chips, and a large battery into a body only a few millimeters thick. There is no room for anything resembling a traditional studio microphone, yet each microphone still has to respond to tiny changes in air pressure quickly enough for speech, music, and environmental sound to be recorded in real time. MEMS technology lets manufacturers place several microphones around the phone without sacrificing huge amounts of space. It also explains why the visible hole tells you so little about what is actually behind it. You are not looking directly at a miniature microphone grill. You are looking at the entrance to a carefully designed acoustic path leading to a sensor buried inside the phone. That tiny sensor solves a modern problem with extremely modern hardware, but the problem itself is much older. The old problem behind a modern phone. Imagine trying to understand someone speaking while an aircraft engine roars only a few feet away. That was not an occasional annoyance for early pilots and air crews. In aircraft and helicopter cockpits, engine noise, vibration, and airflow could make communication exhausting and, in some conditions, difficult to understand at all. Engineers attacked the problem from several directions. Better ear protection blocked some sound physically. Improved communication headsets helped speech remain intelligible. Active noise reduction later used electronics to counter certain unwanted sounds. Those systems did not simply evolve into the microphone processing inside a smartphone. The technologies followed different paths. What they shared was the same stubborn question. How do you preserve the sound that matters when the world around it is loud? Over the following decades, microphones became smaller, digital processors became faster, and sophisticated signal processing moved into compact electronics. Tasks that once demanded specialized equipment could eventually happen inside a device small enough to carry in a pocket. The setting changed completely. A pilot might have been fighting engine roar. You may simply be trying to order coffee while taking a call, but both situations reveal the same engineering challenge. Useful sound is rarely alone. Go back to that tiny opening on the edge of your phone. From the outside, it looks almost meaningless. Behind it is one part of a system that listens from several places at once. Each microphone captures a slightly different version of the same moment. The phone turns those differences into clues, then uses them to decide which parts of the sound deserve more attention. That is the real reason for all those tiny holes. They are not there because one microphone is weak. They are there because hearing from several places gives the phone something much more valuable than volume: context. A feature small enough to disappear beside a charging port is quietly helping the device understand the noisy world around it. Sometimes the smallest details in everyday objects reveal the most invisible engineering. Have you ever wondered what was happening behind that short pause? Tell us which everyday system you want us to uncover next, and subscribe to Small Things for more stories hidden inside ordinary things.